Hi, welcome to Algebra 2 Common Core. Today we're going to be exploring a method for solving exponential equations where the variable is in the exponent. So let's start with some practice problems, some of which may seem very obvious. If I take a look at the first equation, this one is just 2 to the x is equal to 2. I know that my exponent x must be equal to 1 because 2 to the first power is equal to 2. In part B, if 2 to the x is equal to 2 to the third, notice how this equation is set up where the bases of 2 match. So that means that the exponents have to match as well. So that's going to tell me that my exponent x must be equal to 3. It's not necessary to multiply out 2 to the third power to get 8. We just want to make it so that the exponents match each other. In the third example, 2 to the x is equal to 16. What we want to think about is what power we have to raise 2 to get an answer of 16. Well, if you multiply 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, therefore my exponent must be 4 because 2 to the fourth is equal to 16. Now let's go one step a little bit more difficult here where I've got a subtraction problem. 2 to the x minus 64 equals 0. Another way to look at this equation is to take that 64 and add it to the other side of the equation. So I would then have 2 to the x is equal to 64. Again, I want to think about what is the exponent that I have to raise to get an answer of 64. If you again go through the multiplying process, we see that the exponent must be 6. For part E, I'm going to do something similar and say let's move 1 over to the right side of the equation. So 2 to the x is equal to positive 1. Now think about it for a minute and think what your exponent has to be in order for 2 to that power to equal 1. Did you remember that your exponent has to be 0? 2 to the 0 power is equal to 1. Now in F, we're going to see something a little bit more difficult here. 2 to the 3x is equal to 64. In the above problem, we saw that 2 to the 6th was equal to 64. So we could rewrite this as 2 to the 3x has to be the same answer as 2 to the 6th. Now looking carefully, we see that both of our bases are equal to 2. So when the bases match, the exponents must match as well. So we can eliminate the base of 2 for a minute and look just at the exponents. If 3x is equal to 6, dividing both sides by 3, x must be equal to 2. Take a few minutes and go back and make sure that that makes sense to you. 2 to the 3 times 2 would be 2 to the 6th, and 2 to the 6th does equal 64. Now the method that we're actually looking at here is making the bases match each other so that then we could see what the corresponding exponents have to do. So in example G, I've got 2 to the x plus 1. Now 32 is also a power of 2. Think about how many times you have to multiply 2 by itself to get 32. That answer would be 5. So if the exponent x plus 1 has to equal the exponent of 5 on the right side, that would tell us that the missing x value is equal to 4. Now in example H, that's going to be a little bit different because 4 and 8 are not powers of each other very easily written. So instead I could rewrite the 4 as 2 to the second power. But then I'm raising that to the 2x. 8 is 2 to the third power, and I'm raising that to the x plus 3. Now remember your rules for exponents. When I raise a power to an outside power, think about what you have to do with those exponents. We'll need to multiply those exponents together. So on the left side, 2 to the 4x. On the right side, let's take that 3 and multiply it by x plus 3. So that gives me 3x plus 9. Now since the bases are both 2, what we would like to do is set those exponents equal to each other. So 4x is equal to 3x plus 9. If I subtract 3x from both sides of the equation, I get that the missing x value must be equal to 9. You can go back and check that in this version of the equation or in this version of the equation to see that both sides will give me the same exponent on that too. In the next example, I want to examine what happens in an equation when 2 to the x is raised to a power and the answer is 10, which is not a power of 2. So I could go back and look at what powers of 2 I know. 2 to the first power, of course, is 2. 2 to the second power is 4. 2 to the third power, that's 8. Oh, we're getting a little bit closer. 2 to the fourth power, that's 16. And that's too much. That's bigger than 10. So what this tells me is that my x value, my exponent, must be between 3 and 4. So I could either write it out in words between the numbers 3 and 4, or I could write it as an inequality. X has to be an exponent bigger than 3, but smaller than 4. Now in this next example, we are given the graph of f of x equals 2 to the x power. You'll notice that we have some target points on here, 0, 1, because 2 to the 0 power is equal to 1. We also see 1, 2, because 2 to the first power is equal to 2. For all of the examples that we're looking at here, we're going to look in between those values or around those target values. You may want to get yourself a ruler so that you can follow along the lines and see how close you can get to your level of accuracy here. So for example, the first one says, let's find 2 to the 1/4 power. 1/4 is the same as 0.25. So I'm going to draw in a line where I think 0.25 is going to be. I think I've gone a little too far over there, so let me try again. 0.25 will look something like this, and try to make it a nice straight line until you get up to that point. So 0.25 is going to be not quite halfway between 0.2 and 0.4. I'm going to estimate that value at a little bit more than, it might be pretty close to 1.2. So I'm going to say, let's call that one 1.2. And again, remember here, the goal is to estimate these answers. Now for 2 to the 2/3 power, 2/3 I know is 0.66. So on my x-axis, I look for an exponent of 0.66. So I'm going to follow my graph up here and use a value right around there. And that's looking like approximately 1.5. For 2 to the 3/4, oh, that one's going to be pretty close to the one that I just found there. I'm not sure if I can get much closer. So 0.75. I'm having a hard time making my line very straight here. So 0.75 will come up right around there. And it's looking like that's going to be a little bit more than 1.7. Now take a few minutes and take a look at the last 3 of these and see if you can estimate what those values are. Come back and check and see if we are close to each other's answers. Welcome back. See if your answers are close to the answers that I got. I tried to use the graph to estimate as accurately as I could, but then I did do a check on my calculator for each of those exponents, and we were actually pretty close to the estimation. Our estimation was close to the actual value. This is a way of looking at this process in a graphic way. Now, our method of solving exponential equations, doing it algebraically, involves making both sides of the equation have a common base. And looking for this common base is going to be the important part of this lesson. So we want to write both sides of the equation with exactly the same base. So for example, in exercise 1, part A, I see that I've got 2 to the x is equal to 16. Well, this is a pretty easy one, very similar to what we saw on the first page. So I'm going to say 2 to the x is the same as 16, which written as a base of 2 would be 2 to the 4th. When the bases both match, that tells me that I can set my exponents equal to each other. So the exponent that I'm missing here must be x is equal to 4. Likewise, part B is again pretty easy. 3 to the x power is the same as 27, but 27 can be written as 3 to a power. 3 to the 3rd power works out nicely. So x must be equal to 3 in order for the left side of the equation and the right side of the equation to be equal. Now where we start to get a little bit trickier is when it's harder to write the both sides with the same base. On the left side, I already see that I have a 5 to the x. So the question I ask myself is, how can I rewrite 1 over 25 as 5 to a power? Well, I know that 25 is 5 squared. But because the 25 is in the denominator of my fraction, I'm going to have to say that that's going to be 5 to the negative 2 power. So 5 to the negative 2 means take the reciprocal of 5 and square it. So 1 over 25. Notice that all I'm doing is writing an equivalent expression for the right side of the equation. 1 over 25 is equivalent to 5 to the negative 2. So when the bases match, I can just say that my exponent had to be x equals negative 2. Now it's important to kind of get a hang of making these bases the same, because the bases sometimes are hard to look at to decide how do I make the bases equal. For example, in part D, I've got a 16 to the x and I've got a 4. My goal is not to make the 4 become a 16. It's easier to rewrite the 16. 16 is the same as 4 squared. So I'm going to replace the 16 with 4 squared and then raise it to the x power. On the right side, that's 4 to the 1st power. Now again, think about that rule of raising a power to a power. When I've got a power raised to a power, I'm going to multiply the exponents together, so that gives me 4 to the 2x equals 4 to the 1st. Because the bases are both 4, the exponents have to equal each other as well. So 2x must equal 1. If I divide both sides of the equation by 2, I get that my answer is x equals 1/2. That's a solution to the exponential equation. If you go back to check this one, remember we're going back to our original equation, 16 to the x is equal to 4. So we could say 16 to the 1/2 equals 4. Well, that of course is true because 16 to the 1/2 means the square root of 16 is equal to 4. That's a true statement, so my solution must have been x equals 1/2. Let's practice with exercise number 2, where we again are trying to solve the equations by finding a common base. So I look at 8 to the x equals 32. 32 is not a power of 8. So I think about what 32 and 8 are both powers of. 8 is the same as 2 to the third power. So I'm going to replace the 8 with a 2 to the third. Keep the x as the exponent. 32 is really 2 to the fifth power. So now I'm going to say, multiply those exponents, so 2 to the 3x equals 2 to the fifth. Because they both have bases of 2, I set the exponents equal to each other. So 3x equals 5. If I divide both sides by 3, I get that x is equal to 5/3. Now a nice easy way to check this solution would be to store 5/3 in x on your calculator. And then on your calculator do 8 to the x power. You could also just say 8 to the 5/3. And make sure that you get, as your result, 32. Let's practice with part B. 9 to the 2x plus 1 equals 27. Now again, when I'm dealing with exponents, I've got to think about multiplication. So I don't want to say 9 times 3 is 27. Instead, I want to say, what can 9 and 27 both be written as a power of? So 9 is 3 to the second power. And I'm going to raise that to the 2x plus 1. 27 is 3 to the third power. So on the left side, when I'm raising the power of 2 to the 2x plus 1, let's distribute that 2 so it becomes 3 to the 4x plus 2 equals 3 to the third. Now when the bases match, I can set the exponents equal to each other. So 4x plus 2 is equal to 3. Subtract 2 from both sides of the equation. So 4x is equal to 1. Dividing by 4, x is equal to 1/4. Now again, it'd be a nice easy way to check this by storing 1/4 in my calculator for x, and then in my calculator doing 9 raised to the 2x plus 1 to be sure that you get an answer of 27. Now looking at exercise C, I've got 125 to the x equals 1 over 25 to the 4 minus x. Think about what power I can, well actually think about what base, what number do I multiply by itself several times to get 125 and also 25. 125 is the same as 5 to the third power. I'm going to raise that to the x. 1 over 25, we talked about that a few minutes ago. That's 5 to the negative 2 power raised to the 4 minus x. So when I'm raising a power to a power, I multiply the exponents. 5 to the 3x equals 5 to the, let's distribute the negative 2, so I get negative 8 plus 2x. Now again, the bases are both 5, so I'm going to set the exponents equal to each other. 3x is equal to negative 8 plus 2x. Subtracting 2x from both sides, I get that x is equal to negative 8. So the solution, the only answer that makes my original problem, 125 to the x equals 1 over 25 to the 4 minus x, true, is the number negative 8. Now to check that solution, I would have to substitute negative 8 into both sides of the equation for x, and then use my calculator to do the left side, and then use my calculator to do the right side, and make sure that the two sides have equivalent answers. If you have any questions about this, please come and see me in the morning. In exercise number 3, it says, which of the following represents the solution set to this equation, 2 to the x squared minus 3 equals 64. So I see that I have an exponential equation. On the left side, my base is 2. It's raised to the x squared minus 3. Well, 64 can also be written as 2 to a power. In fact, it's 2 to the 6th. So when these bases of 2 match, I'm going to set the exponents equal to each other. So x squared minus 3 is equal to 6. Let's add 3 to both sides of the equation, so x squared is equal to 9. This is a quadratic equation that should have 2 solutions, so I'm going to square root both sides of the equation, but on the number side, remember that we always want to put in a plus or minus. So my solutions are x is equal to plus or minus 3. So my solution set would be choice number 1. Let's do one more example together, and then I'm going to give you some time to try some of these problems on your own. In exercise number 4, it says at what x coordinate will the graph of y equals 25 to the x minus a intersect the graph of y equals 1 over 125 raised to the 3x plus 1? So we've got a few things going on in this problem. We've got 2 graphs and we want them to intersect with each other. Well, if they're going to intersect, that means that their y values must match each other. So I want to know where 25 to the x minus a will equal 1 over 125 to the 3x plus 1. So you'll notice that this is just an exponential equation whose variable is in the exponent. It's really important to note that part because we're going to have other problems tomorrow where the variable is in a different spot. So for this one, I see that my bases don't match. So I want to think about what number 25 and 125 can both be written as a power of. 25 is 5 to the 2nd power. So I'm going to raise that to the x minus a. 125, well, 1 over 125, because it's a fraction, that tells me I'm going to have a negative exponent. 125 is really 5 to the 3rd, so 1 over 125 should be 5 to the negative 3rd power. Raise that to the exponent of 3x plus 1. Use our rule for multiplying exponents, so I'm going to say 5 to the 2x minus 2a is equal to 5 to the negative 9x minus 3. So in both cases, on the left and the right, do that distribution, 2 on the left side, negative 3 on the right side. Now, both bases are 5, so I'm going to set the exponents equal to each other. Hopefully by now that looks very familiar to you. Now you'll notice that I actually have 2 variables in this problem. I've got the variable of x, but I've also got the variable of a. We want to find the answer for the variable x. So we want to put our x terms together. So I want to add 9x to both sides of the equation. That's going to give me 11x minus 2a equals negative 3. Since I'm solving for x, I'm going to add 2a to both sides of the equation. So 11x would be equal to 2a minus 3. Finish it off by dividing both sides of the equation by 11. So when I divide both sides by 11, I'm getting an answer of x equals 2a minus 3 over 11. You should notice that this is choice 2 for my multiple choice answer. So look this example over because it's one of the most complicated that we have seen today. I'd like you to write down these 3 you try it's in the you try it box in your notes. Then go ahead and pause the video and solve these three exponential equations. When you're done, come back and I'll go through a short explanation for each of them. Hi, welcome back. Check your work over with my work. See if your solutions match. And again, remember that each of these solutions can be checked by substituting the value of x into the equation and making sure that the left side of the equation and the right side of the equation match each other. You'll notice in example number 1, we could easily get the exponents to match if we used a base of 2. 128 is just 2 to the 7th power. In example number 2, we wanted to write both 3 and 27 as 3 to a power. So the left side we kept exactly as the original. On the right side we had to replace the 27 with 3 to the 3rd power. Then of course use your rule for raising a power to a power. So multiply those exponents together to get 3x plus 3. When the bases match, we're going to set the exponents equal to each other and solve for our answer for x. Example number 3 is a little bit more difficult because 4 and 32 can't easily be written with the same base unless we go down to a 2. 32 is not 4 to any power that's an integer. So what we're going to say is let's change the 4 to 2 to the 2nd power. Let's replace 32 with 2 to the 5th power. On the left side, let's multiply the exponents 2 times x minus 4 to get 2x minus 8. On the right side, let's distribute the 5 times x plus 1 to get 5x plus 5. Because the bases match and are equal to 2, I can set the exponents equal to each other. So 2x minus 8 is equal to 5x plus 5. Solving for x, I end up with the solution x equals negative 13 over 3. And again, go ahead and store that value in x on your calculator. Type into your calculator 4 to the x minus 4 and get the answer. Then also type in 32 to the x plus 1 and see that both of those answers match each other when my solution is x equals negative 13 thirds. Please, if you have any questions on this process, come and see me because it's really important that you understand what we do to make the bases equal to each other. This is called finding common bases. Have a great night, and we'll see you in class.